Okay, we're just setting up some technical things here.
I assume you want speaker notes, right?
Whatever. Yeah, that's good. Perfect. There we go. Okay, I think we're going to dim the lights. As we get started here, I have to say it's rather wonderful to be in front of an audience like this. This was not actually the kind of audience I was expecting at all, I have to tell you. But it's absolutely wonderful. Thank you so much for coming this evening. So it occurred to me as I flew in on a plane from New York this morning, it occurred to me as I was on the plane that today is October 4th. And October 4th in 1957 marked the occasion of the first artificial satellite placed into orbit around the Earth. That is Sputnik 1. It was launched on this day in 1957, which is a rather wonderful coincidence. And it matches a little bit of what I'm going to talk about in the next 25 minutes or so, which is to do with the nature of space exploration, but from a somewhat more sophisticated standpoint than perhaps it's usually discussed, and that is through the lens of what we call astrobiology. And astrobiology is the study of the nature of life in the universe. And so you may wonder why that, or how that could possibly connect to space exploration. So my task is to show a little reverence towards space exploration, but also to have some fun tonight. So let's make a start. And I thought I'd begin with this image. Now, a few of you in the audience may recognize this image. For the rest of you, you're wondering what on earth this is. It doesn't look very exciting. But since this is the Sagan lecture, I'm going to start by using Carl Sagan's own words to describe this image. I'm actually going to read it out. Carl Sagan wrote in his book, Pale Blue Dot, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species live there on a mote of dust suspended in a sunbeam." So this image of the little dot that you might just be able to see roughly where I'm pointing on the screen, that little pale blue dot, is the Earth. And it's a very famous image. It was taken in 1990 when the spacecraft Voyager 1 turned back and took a portrait of the planets of the solar system. At that point, it was 6 billion kilometers from the Earth. Today, Voyager 1 is still going, and it is over 23 billion kilometers away. And it's a part of our planet that will never get back again. And that speaks to something really fascinating about what's happening here on Earth. After 4 billion years, life on Earth has found a way to escape through us, through our technology. This little animation is a representation of satellites in orbit around the Earth today. It's a highly exaggerated representation. But the reason for that is because there are a lot of things that we've placed into orbit just around our own planet. In fact, since 1957, since that famous launch of Sputnik on October 4th, 1957, over 6,800 non-commercial spacecraft have been launched, and today there are over 4,500 operating commercial satellites in Earth orbit, and over 1 million pieces of debris larger than 1 centimeter. There's a lot of stuff that used to be on the Earth and is now out in space. And we're getting really good at this. We've been pretty good at this for a while, but we're getting better and better. Our spread into space is very sophisticated and it is accelerating. We have launch systems, go back to the Saturn V rockets on the left there, European Space Agency launch system, Space Shuttle when that's operating. Now companies like SpaceX doing mind-boggling things with their boosters that come back and land to be reused. And it is accelerating. In 2010, about 100 spacecraft were launched away from the Earth. In 2021, over 1,600 spacecraft were launched. There is an accelerating process of launch into space. At the same time, we of course have learned just how incredibly hard it is to explore and certainly to exist beyond the Earth, certainly to exist as living human beings and for other organisms on the Earth to live and propagate beyond the Earth. But even our technology has to be built very, very carefully to be able to function beyond. Everything out there wants to kill you or your machines. So you can't see it terribly well in the lower panel, but there's actually a little sunrise taking place. Sun is somewhere down here. This is sunrise on Mars, the image taken by the Spirit rover. And it's a very serene landscape, but it's a landscape that definitely wants to kill you and your machines. Mars is not a pleasant place. It's beautiful, but it's not pleasant. At the same time, our virtual access to the solar system and other places is increasing, and it's increasingly rich and dynamic. I'll show you a couple of little videos here. These are from the Mars 2020 Perseverance rover landing on Mars. It's truly remarkable. Let me just play both of these. One set of videos at the top shows you parachute open to help the capsule containing the rover descend to the Martian surface. The lower panel show the moment at which the rover was lowered right down onto the Martian surface, blowing away the dust by a sky crane, which you see in the central panel there. The sky crane hovers, lowers the rover on a cable, drops it, and then flies off, go and crash itself somewhere to make garbage on Mars. We've definitely increased the amount of garbage on Mars. Those are remarkable videos, right? It looks like something you watch on Netflix, but those were actually taken during this process of landing the rover on Mars. We have an extraordinary virtual access to the solar system that continues to be more and more remarkable as time goes by. We have information from truly alien places flowing back to the Earth. It's not just that we're putting things out into space, we're also receiving information that arguably no other species before us on Earth has had the capacity to receive. For instance, this little loop animation is an animation of frames taken, real images taken by the Rosetta spacecraft around 2015 as it orbited a cometary nucleus out in our solar system. You can see in the backdrop, there's a star field, there's the stars of the Milky Way galaxy flying by because the cometary nucleus is tumbling through space. The spacecraft is tracking the nucleus. There are specks of light. Some of those specks of light dashing across the frame are particles of dust and ice being illuminated by sunlight. Other specks or streaks are actually because of cosmic rays, charged particles hitting the internal pieces of the camera and the spacecraft and depositing charge to create that image. It's a very spooky looking image. On the right here is a pieced together animation using still images taken from a different space probe. This was the Huygens probe that descended onto Titan, largest moon of Saturn, back in 2005. As it descended on its parachutes, it actually took quite a long time. This is a somewhat accelerated view of things, a set up view. It took images that were pieced together to give us the experience of landing on this moon that is so cold that hydrocarbons like methane and ethane are in liquid form. There are entire cycles of of hydrocarbons evaporating and raining out on the surface, forming lakes and rivers. The rocks that Huygens crunched into are probably made of water ice, because at these temperatures, essentially water takes the place of silicate and carbonate rocks that we might experience on the Earth. So I had fun putting this together. This little mosaic, each image corresponds to a successful landing or impactor experiment on the surface of other bodies in our solar system. This is pretty much all of it over the last 60 years or so. It took me a few hours to trawl through, Wikipedia is a wonderful thing, trawl through and put this together. And there'll be many failures as well, which are shown here, and a few extra ones that I didn't put on. And then, of course, many spacecraft that were never designed to reach the surface of other bodies. But we've been on the surface of Venus, been on the surface of Mars, of course, been on the surface of asteroids, cometary nuclei, and most definitely the moon, including when humans walked on the surface of the moon during the Apollo missions in the late 1960s and early 1970s. It's pretty remarkable what we've done. In that sense, it should be celebrated. But I mentioned astrobiology. What I think we're seeing is a fundamentally astrobiological phenomenon here. Remember, astrobiology is the science of the nature of life in the universe. Humans have dissolved the wall between worlds, which is a very strange and remarkable thing. And in doing so, they've created the opportunity for life and life structures to be exposed to entirely new environments, other places in our solar system. We may not have put that many humans out there, but we put a few, and we're going to put more, and the humans carry things along with them. But it's also our technology goes into these new environments. And as I mentioned before, there's a reverse thing taking place here, where information can now flow back to our world, information that we couldn't have obtained in any other way. And I think the second speaker this evening, David Grinspoon, will talk a little bit more about this. But the information we get from our presence in space helps us understand the Earth far better than we could have otherwise. It helps us monitor the weather, it helps us make decisions about where to plant crops, it helps us understand natural disasters and perhaps avoid them, it helps us understand the functioning of our sun, shown on the right there. Our sun can send out great plumes as material, mass ejections, solar flares that influence the atmosphere of the Earth, but can also be incredibly disruptive to our technology by inducing massive currents flow through our power grid, and even through conductive rock. That this part of the world has some of the more susceptible rock types to things like solar storms, where enormous currents can flow and be destructive for our technological world. But the real question I want to get at a little bit this evening is what really happens to a species, maybe to us, but maybe other species that could be elsewhere. What happens to the species and life on a planet in general when it gains this access to the rest of the cosmos? Well, it's clear that it involves developing new forms of reach. Now, in evolutionary biology terms, this is a very technical term, we might call this extended phenotypes. It's a different kind of expression of genetic material, and it changes because the environment changes. I would count our technology as a type of extended phenotype. It's an extension of ourselves. It's structures that originate ultimately from our genetic material, but of course will take on almost a life of their own. And there are new niches to evolve into. So let's do a little thought experiment. This is kind of the fun and crazy part of my talk. Let's just do a little thought experiment. So in science, when you have a question like, what really happens to a species as it dissolves the walls between its home world and the rest of the universe? In science, when you have a question like that, for which you really don't have yet a good answer, one thing you can do is figure out the extreme possibilities, the bracketing extremes. the envelope of possibilities. And I would say our future has two possible extremes. Then somewhere in between those extremes is perhaps where we'll land. Those two extremes are that from now on, there's zero interplanetary growth. That having done a bit of space exploration, having launched some things and put a few people on the moon, maybe we decide tomorrow that we don't want to do that anymore. Maybe we turn inwards, decide that the problems here on Earth deserve our focus exclusively. So we have an Earth-first outlook. That's one extreme. The other extreme is maximal interplanetary growth. That's kind of the cool stuff I want to talk about a little bit for fun. And it's a thought experiment. So let's do this thought experiment. This is basically, we're doing a science experiment in our heads. So we can ask the question of exactly how much life could the solar system support? This is going to sound a little bit like science fiction, but I'll walk you through it, then sort of try to bring it back to reality at the end. So what do we need to understand to gauge how much life the solar system could support? Well, there are two main constraints for things like living organisms, and that's matter and energy. You need matter to build stuff, and you need energy to drive it. That's not an exclusive requirement for life. Other things require that too, but it works well for life. So matter and energy. Let's think about the matter first. So for terrestrial life, it turns out there are certain elements, things like phosphorus and nitrogen, that are absolutely essential for biochemistry as we understand it. Particularly something like phosphorus, which forms a part of the backbone of DNA and energy-carrying molecules in our biochemistry. But things like phosphorus and nitrogen are somewhat rare. They're not so easy to get a hold of out in the universe as a whole. So if we can figure out a good source of those elements, that kind of tells us how much stuff we could ever build out of all the matter that's in our solar system. Elements like carbon and oxygen are much more abundant, so they'd sort of come along for the ride. So let's say we repurpose the asteroids. So this is where it starts to get crazy. In our solar system, there are at least 100 million or so-called carbonaceous bodies. These are asteroids that are very rich in carbon and rich in other elements like nitrogen and phosphorus. Well, if you sit there with a piece of paper and work this out, and forget that it's all sounding kind of crazy, you can determine that just from the 100 million or so carbonaceous bodies in our solar system, you could produce roughly 6,000 planetary biomasses. So if you add up all the stuff on Earth, all the living material on the Earth, you could make 6,000 times that amount of living material if you could harvest necessary elements from these asteroids that are floating around or orbiting around in our solar system. Okay, 6,000 planetary biomasses. So what does that mean in terms of humans? Well, let's suppose as well, scientists love doing this kind of thing, sort of back in the envelope calculation. Let's say that it takes an entire planetary biomass like the Earth's to support the current human population at around 8 billion. Now, we're probably a few too many of us, but let's just assume that that's what's necessary to support roughly 8 billion humans. So the solar system, just by harvesting this asteroid material, could grow about 50 trillion humans. There you go. Obvious, right? Easy. Let's think about the next piece of this. What about energy? Well, the sun is the single greatest source of power in our solar system. It outputs around 380 trillion watts. That's power flowing in all directions away from the sun. Now, the Earth, of course, does not receive or utilize anything but a small fraction of that. So in fact, Earth, a little planet orbiting the sun, only intercepts about 1/10 billionth of the total output of the sun, about 173,000 trillion watts, and about 30% of that gets reflected right back out into space. And just to put it in context, human power use right now, which a lot of it involves things like hydrocarbons, which are arguably generated because of solar power originally, but we won't get into that. But the human power use right now represents about 1/10,000th of that. So we might think we're running out of power, but we aren't. The question is, how can we utilize all of it? So we can do the next bit of this little thought experiment. Say, let's assume that you need the same amount of power that the Earth currently intercepts from the sun to run a full Earth-like biomass. So that means that the sun, in principle, if you could capture all of the energy flowing out from it, all of the power, you could support 10 billion Earth analog worlds. And I have to say, this image, I tried to generate using an AI art generator, and it was incredibly difficult. Writing in things, show me 10 billion Earth-like planets, and it would just show me one planet. Show me 100 Earth-like planets, that showed me one planet, and so on and so on. I was clearly using the wrong algorithm. This is about the best that I could get it to come up with. It's kind of surreal and nice. So if you have enough power to support 10 billion Earth analog worlds, then in principle, the solar system and the sun has enough power to support the planetary environments capable of holding 80 million trillion humans. So in other words, we might run out of the material needed to make humans and their associated biomasses long before we run out of energy or power. So at this point, you're wondering where this is going. Well, there's a couple of slides here. People have thought about this before. Most famously, physicist Freeman Dyson, quite a few decades ago, took this idea and said, well, you could do this if you just repurposed Jupiter. So this is a sort of conversation you had with someone after you've been at the pub for a while. Dyson said, well, all the mass in Jupiter could be repurposed to build structures that would essentially encase our sun and capture all of its energy. And in fact, if you did this and encase the sun somehow, not in a single monolithic structure, because that would not be gravitationally stable, it would have to be lots of orbiting structures. If you place these structures out at Earth's present orbit to encase the sun, not only would you capture all of the sun's power, you would also provide about 550 million times Earth's total surface area to live on. And what would that mean for 80 million trillion humans? Well, there would be about 290 people per square kilometer. And that's similar to the average population density of Connecticut in the US. I looked at Ontario, and there are far fewer people in Ontario per kilometer square. So, okay. So you could live quite comfortably on this real estate, 80 million trillion human beings, plus all the biomass necessary to support them. This is clearly all absurd, crazy stuff, right? And I wouldn't argue with that. But the reason for going through this rather absurd sounding argument is to say that the interesting thing is it's so extreme, the possibilities are so extreme, that it's saying that almost anything between where we're at now and that extreme, almost impossible future is going to be about an extension of life's environment on completely unprecedented scales. Scales we just haven't conceived of yet. And we're not talking about the 80 million trillion humans, but anything even remotely towards that possibility is going to be on extreme, extreme scales. And that will have profound implications, or could have profound implications for the future of life. So here's a couple of examples as I get towards the end here. Let's imagine the future where life extends from the Earth, humans and other things go along with the humans, into environments that are very different and much, much larger in scale than anything that life on Earth has encountered in the last 4 billion years. So perhaps the future is about distinct new traits and distinct new species of humans and other organisms. So to use an example from the Earth, these are the Galapagos Islands, which some of you may know about because they're part of Charles Darwin's voyage on the ship Beagle. He went around the world and he visited various places, including the Galapagos Islands in the Pacific. And the remarkable thing about the Galapagos was that for him, it made very clear certain things about the nature of evolution and the possibility for life to spread into environments. So he had these famous finches. I bet you weren't expecting a picture of finches in a talk about space exploration. Darwin's finches are essentially from the same underlying lineage, but show remarkable differences in adaptations across different environments, sometimes on a single island in the Galapagos set of islands, but sometimes across different islands. And it helped Darwin see that adaptation was an essential feature, what he came to call his theory of evolution, this ability to adapt things like beak size according to precisely what kind of food was available at a given time, to adapt really quite quickly. These finches adapt really fast when things change. Climate is always changing in the islands and so on. Maybe that is a marker, is an indication of what could happen to life as it spreads beyond the Earth. Beyond the Earth is an environment that, as far as we know, certainly terrestrial life that originated here, has not experienced before. Then another idea is that perhaps the dilution of humanity across space and time, if we do continue to expand in any way from our present situation, could it actually fix some problems? Right? Some of our biggest concerns today are about interaction around the globe. We've become a globalized species, and that has many pros, but also many cons. And it's possible, though, that simply diluting us could help. So in science fiction, there's often scenarios talked about where we imagine Earth is occupied by Earthlings and Mars is also occupied by people who came originally from the Earth. So we have wars between Earth and Mars. We have, Mars Corporation doing things that we don't want it to, and so on and so on. It's famous fodder for science fiction. But maybe that doesn't happen. It's a long way between these two worlds. And even light travel times are significant. On average, it can take about 20 minutes for a round trip message. We don't know what that kind of dilution in space and time will do. Maybe we end up just not caring about each other, right? Mars does whatever Mars does, and we do whatever we do back on the Earth. It is possible that this dilution could fix some of the problems, some of the social problems, some of the problems of inequality that affect us today. Okay, I'm almost done. So I just want to end by saying we do face genuine existential crises, but we also can't afford to ignore possible futures where our lineage, and I mean humans, but also everything else on the Earth, all the other living things on the Earth, because we are ultimately all of the same lineage, extends into the cosmos. We can't ignore that possibility. It's a more optimistic outlook on the future than perhaps we're used to these days. And so I feel it's appropriate to end with one other quote from Carl Sagan. This is also from his book, Pale Blue Dot. And it says, "The visions we offer our children shape the future. It matters what those visions are. Often they become self-fulfilling prophecies. Dreams are maps." Thank you very much. I think there is another talk coming this evening, but I don't know if we have a short pause. So there is definitely another talk happening in maybe 5 minutes.
Yeah. Yeah, sure.
Oh, my pleasure. Thank you. Oh, what's this? Trillion has 12 zeros. A million has 6 zeros. 12 plus 6 is 18. Plus 3 other zeros. I think it's 19 years.
Yeah, folks, we're gonna take about a 10-minute break and then we're gonna have another speaker. We started.
Okay.
Yeah, yeah. I mean,
Okay. Okay. Go visit the other room.
I really want to ask. Gentlemen, so gentlemen sitting closest to us, great. Yeah. But here's the principal investigator, mission.
Okay, I was gonna make everyone run it.
Can you grab my slides? Because I might just show the beginning of the thing,
Sure. Let's see.
if I can do it, but I think I should do it with the lights on. Because I really want to do is talk to the kids.
Still showing the screen? I'm still showing the screen. Your presentation.
So I'm curious how bright it would be with the lights on. I would switch it to whatchamacallit mode.
Presenter somewhere. Then I'll show full screen here, but then you'll have your notes down here.
Yeah. It's gonna work because what I really want to do is go to this, and then I'm gonna do lights on and we can talk.
Yeah, I think that's great. I appreciate it. Thanks for being flexible.
We'll figure it out. Yeah. The kids are great. So
Yeah.
when we're middle of the sense.
Yeah.
Yeah. That's good. It's good. We're good. We're good.
Whether you want to do it, I'll give you my special.
Question for my friend because like he's like really good at that. But he was wondering what you had to do in order to get into like access to it. He's like really interested in, you know, like high school and So like, never. One of which. I have How?
Let me take a picture, right? You waited. All right. Hey, kids. Hey, my name's David, and I'm here in London, Ontario this week with some of my friends because we love planets. And all of our friends that love planets, we get together once a year in a different city just to talk about planets. And we love them so much that some of us, that's what we do for a living, is that we send spacecraft to other planets and we get back pictures and other information, and we try to figure out planets. And so that's why we're here. And it's really cool that we get to be here in London with you. I'm just curious, do any of you love planets? Let me ask a question. Raise your hand if you have a favorite planet. Wow, what's your favorite planet? Good planet. What's your favorite planet? Pluto. Does anybody know what this little planet is? What is it? It's what? Yes, it is a dwarf planet. See, I just thought you were going to say Pluto, but you're way ahead of me. He's right. This is Pluto, and it's a dwarf planet. The fact that we can look at this picture right now and see all of these planets together and compare them like a family is pretty amazing. We live in an amazing time because if you were a human being, say 100 years ago, you might wonder what the planets are like. You could see them in the sky. You could maybe look at them with a telescope, but you wouldn't have pictures like this. We're really the first humans who have sent spacecraft to all these planets, and now we can look at them as a family and think about what's similar and what's different about them, and we do what's called comparative planetology. In fact, I think I even have a slide about that. See, comparative planetology. That's what my friends and I do. We look at the planets and we say, well, these two are kind of alike. Venus and Earth are the same size. This one, Mars, is a little bit smaller. But then we say, but they're not exactly alike because Venus is really, really hot and Earth is much cooler. But why? We measure them and we try to figure out why are they similar and why are they different? And that's what we mean when we say we're doing comparative planetology. Now, I got a bunch of slides lined up here to talk about tonight. And honestly, they maybe aren't the right slides because I thought I was going to be talking to more adults, but I'm actually really happy that there's kids here because I love talking to kids. Actually, let me show you. I'm going to show you just a couple of my slides, and then I'm going to stop and we're just going to talk to each other, okay? But I want to turn off the lights for a second because I want to show you one thing that's kind of cool. When we talk about comparative planetology, one of the things we do is we look at what's similar and what's different on these worlds. So here, these are three of my favorite planets. Venus, and I'm with you, Earth is probably my favorite if I had to pick one, but I really like it here. And Mars. What's cool about these planets, Venus and Mars, are our closest neighbors. And in some ways, they're very much like the Earth. They're rocky surfaces, they have atmospheres. In some ways, they're different. But with comparative planetology, we can look at features that are familiar on the other planets and yet different. So for instance, you know what this is? We call this a river delta. It's where a river is flowing and then it runs into a lake or an ocean and it sort of fans out and makes this fan shape. And here you see river deltas on Venus and on Earth and on Mars. And in some ways, you can see they're familiar, they're similar. They all have that shape where there's a river and then it fans out. And something else. So we see that nature doing the same thing. And if you look, you can see that they're all different. And the ways in which they're different tell us something about the story of that planet. So we look at these and we start learning the stories. For instance, when we see this river delta on Venus, and we learn about what it's like on Venus, we realize this was not carved by flowing water. Why? Because it's so hot on Venus. It's like 900 degrees all the time. It's like inside your oven turned all the way up. So it cannot be water. All water would boil. So what is it? It's some kind of lava. It's like liquid rock that's so hot it melted that floated on the surface. And then we look at this river delta on Mars, and it was carved by water, but if you look closely, you start to understand that this was carved billions of years ago, that Mars, this is a planet that had flowing water way in the past, a long, long time ago, when the planets were just young little baby planets. How do we know that? Well, if you look carefully, you see at the top, it's sort of eroded, like ancient, it's worn down by billions of years of weather. And you see that circular feature right there? There's craters on top of this. And whenever you see craters on something, that also tells you this is really old. It's been sitting there getting hit by stuff from space. So we see one planet where it was too hot for liquid water. We see one planet where there was liquid water billions of years ago, but it has not had any water since then. And then when we look at the delta on Earth, if you look at it carefully, what you see is that it's completely altered by life. And everything on Earth is completely altered by life. If you look closely at this picture, you see that there's colors and forms. This is actually where there are mangroves, which is the kind of forest that grows on river deltas. And so we see one planet that's completely altered by life, one planet that's way too hot for life, and one planet that dried out billions of years ago. So that's just one example of how we do comparative planetology. We look at the same thing on different planets. Now, here's the thing. The thing about planets that makes it hard to study them is planets are not like plants. I know it sounds almost the same. If you add an E to plants, you get planets, right? But if you have an idea about plants that you want to study, you can do what we scientists call a controlled experiment. When I say controlled experiment, what I mean is, hey, I have an idea about this plant. I think that if I change the soil, I put more nitrogen in the soil, or I'm going to give it more water, or I'm going to give it less water, or I'm going to give it more of a different kind of light. This is my theory, my idea, my hypothesis, my idea that I want to test about this plant. Then I can try it. And if it doesn't work, I try it again. And I do it in one example, and in the other one, I do something different. That's what we call a controlled experiment to test our ideas. But with planets, if I have an idea about how planets evolve, I cannot do a controlled experiment. Why? Because I don't have 4 billion years to wait around and try again. And I don't have very many planets. So with planets, we're sort of stuck with the ones we have. We can't do controlled experiments. But this is why I'm so happy we have Venus and Mars near Earth, because they're almost like controlled experiments. Like there are other planets, they're kind of the same, but they have one thing a little different. Venus and Earth, we think, started out the same, but Venus was much closer to the sun and it got much hotter, and its climate changed. Earth and Mars started out similar, but Mars was much smaller and its atmosphere escaped into space. So this is like the closest we have to a controlled experiment. And that's kind of what I mean when I say comparative planetology. But what I want to do now, instead of just showing you more slides, is turn the lights back on and just see if you guys have any questions about planets that me and my friends here might be able to answer. So I see one hand. Yeah, you have a question? Sometimes the Earth just comes to the moon and then to the sun. Yes, exactly. The Earth is spinning around, like in this, you're talking about how the Earth spins, right? So if you're standing on the surface of the Earth, it looks like the moon is rising or the sun is setting, right? But really what's happening is you're just spinning, like if you're, say you're the moon, right? And I'm the Earth, and then I'm doing this, and then like, look, you're rising. Now you're setting. Whoop, now you're rising, now you're setting again. So exactly, it's because the Earth is spinning that you're seeing that happen. Very good point. Oh, we had a question back here. Thanks, Brian.
Why yesterday you can get Jupiter and the Saturn and the moon and a lot of the other things, but not every day you can see those. Like it seems like not every day you can see those, like all of those at the same time.
Great question. So why is it that today you can see the moon and Saturn and Jupiter, but not every day you can? Yeah, that's a great question. I think we ought to act this out actually. Henry, come up here if you don't mind, and Caleb. Let's see if we can do this, okay? And Brian. All right. Now, let's see. I'm Earth. You guys see Jupiter and Saturn. and you be the moon, okay? So you guys are going really slowly around the sun. Wait, we need a sun. Alan? All right,
You can all orbit me.
all right, the sun's in the middle, okay? You're right there.
Okay, good.
And you're the moon, so you're orbiting me. And these guys are orbiting really slowly, and we're going faster. Here, you gotta turn circles around me. Go, 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 go. Yeah, exactly. See? So as the days go by, see, those guys are orbiting really slowly, right? And I'm spinning the day. So there, the moon's up. Now the moon's down. Oh, now Jupiter and Saturn are up, right? But now, when I'm here, see, now I cannot see Saturn at all for months and months because Saturn's on the other side of the sun. See that? But the moon is always there and it's always going around me. So it's like it's up, it's down, it's up and down. But Saturn is going to be a long time before Saturn is back. Jupiter is going really slowly. So when Earth comes around here, like right now, Jupiter is in opposition, which is when Jupiter is the closest to us. That's because Jupiter is right there and Earth right here and the sun is right there. You see that? And now it's going to be a long time, again, years and years before we're in the same configuration. Anyways, we don't have to keep going here. Thank you, sun. Thank you, moon. Thank you, Jupiter. Thank you, Saturn. But you get the idea, right? It's all because of the different rates at which things are orbiting around the sun and the moon is orbiting around the earth. I hope that helps. We had fun anyways. Any other questions? Yeah, over here.
Do you think Pluto is a planet or not?
Do I think Pluto is a planet or not? Yes. Are there any other questions? No, let me tell you why. You've heard people talk about, oh, Pluto's not a planet anymore. Pluto is a planet. It's all a little bit silly, honestly, because what's really important is what's interesting about Pluto. The fact that Pluto is this icy, beautiful, round, wonderful world with an atmosphere and mountains and glaciers that we visited with a spacecraft called New Horizons. And by the way, the guy who was in charge of the New Horizons mission to Pluto is in this room. I don't know if I should embarrass him, but it's Alan Stern right there. He is Mr. Pluto. Yes. But I'll tell you what. It's like, what do you, it's sort of, if there's a mountain out there and somebody said, that's not a mountain, it's a hill, right? Because mountains are bigger than that. It's all sort of silly. Well, it's bigger than other ones. What do you care what it's called? But the thing is, the people who feel that Pluto is not a planet, they're thinking about the orbits, the way that things orbit around, and the way that some people think that Pluto's not a planet because its gravity doesn't push other planets out of the way enough. And therefore, you need to, in order to be a planet, you have to have enough gravity to push other planets out of the way. But a lot of us think that that's not right, that what makes something a planet is if it's a big, round, interesting object. And you know how, I don't know if you saw in there that they have the little models of asteroids and comets and the game in there. All the little things in the solar system, like asteroids and comets, the things that are maybe just a few miles across, they're lumpy, they're potato shaped. But whenever something gets big enough, hundreds or thousands of miles across, it's always round. You ever think about that? Why is it round? It's because of gravity. You know why, right? Because of self-gravity. Anything big enough, just like a droplet of water falling through the air, pulls itself into a round sphere. Anything big enough to have enough gravity will always be round. So a lot of us think that that should be what makes something a planet. And if you think that way, which I do, then Pluto is a planet. So I'm going to go with yes, it's a planet, but not everybody agrees with me, and that's okay. Yeah.
Which one is bigger?
Wait, I'm sorry.
Which one is bigger, Earth or Venus?
Oh, which one is bigger, Earth or Venus? That's a great question. Because what's cool about Earth and Venus is that they're almost exactly the same size. Earth is a little bit bigger than Venus. In fact, if Earth was the size of a regulation basketball, which if I had one right here, I'd show you how good I am at dunking. But if Earth is the size of a basketball, then Venus is the size of a soccer ball. It's just slightly smaller. But what's amazing about Earth and Venus is that they're almost twins. We don't know of any other two planets that are so similar in size. But it's a good question. So the answer is Venus is slightly smaller. Yeah. Go ahead.
Okay, so why gravity that? Couldn't it be like square, triangle, or whatever?
Yeah, that's a good question. Why does gravity make everything so round? Why couldn't it be square or triangle or whatever? You know, gravity is what we call sort of a fundamental force in the universe. It's very simple. Every single piece of matter in the universe, which is everything's made out of matter, right? You're made out of matter, this or every bit of matter in the universe attracts every other bit of matter in the universe's gravity. And the more stuff there is, the more it attracts, the more it pulls. And just because of that, it means that if you gather a bunch of stuff together, it starts pulling more stuff towards the center. It's because gravity pulls everything towards the center when you have a bunch of mass together. And that pull towards the center makes everything round. I don't know if I can really explain it better than that, but it's a really good question. Yeah.
Become a dwarf planet.
How did Pluto become a dwarf planet? Well, I mean, before the planets were planets, they were what we call planetesimals, which just means little baby planets. And the planets formed by smaller pieces crashing into each other and making bigger pieces. And basically, Pluto became a dwarf planet when enough ice and rock crashed together to turn it into a round ball because of gravity, like we were talking about. And then once that happened, then Pluto was a dwarf planet. Does that make sense?
Why is it that Venus has stripes and Earth is swirling?
So I think I understand what you're saying. Why does Venus have stripes and Earth has swirl? Because of the way they rotate. So Earth is a fast rotator, meaning that it rotates once in 24 hours, right? Which is fast compared to some planets and slow compared to other planets. But it's fast enough so that the weather patterns, because of the rotation of the Earth, get pulled into those swirling, like those cyclones, like hurricanes, storms, and basically all weather patterns are swirls. Venus is a very, very slow rotator. It takes hundreds of Earth days for Venus to rotate. It goes very, very slowly. And because of that, the air patterns, the weather patterns are different. And it ends up being that they're less influenced by the solid rotation of the planet and more just influenced by the sunlight pushing the atmosphere around. And that basically is why Venus has that more stripy appearance and Earth has that more swirly appearance. Does that make sense? Cool.
Like, why do the planets have to spin around the sun? Why can't they just spin around like Venus or stay still?
Yeah. Why do planets have to spin around the sun? Why can't they just stay still? Yeah, well, the thing is, it's because they started out, everything started out as like a disk, a swirling disk of material. When the baby sun was born, the baby sun was born from a collapsing, spinning cloud of stuff. So there was a cloud in space that was spinning and spinning and spinning. And the planets formed out of that cloud. And so when the planets formed, they were spinning and orbiting around the sun like that. And in space, there's no friction. There's nothing that stops you once you're moving. So if you start out orbiting something, you're going to keep orbiting something. If you started out a planet not orbiting the sun, then it probably wouldn't orbit the sun. It would just sit there, or it would fall into the sun, or gravity would pull it somewhere else. But it's because of the way the planets formed from a spinning disk that makes them, they started off orbiting, and there's nothing really to stop them, because in space, there's no friction. Like if I'm on Earth, if I'm going through the air will stop me. It'll slow me down. Or if I'm skidding along the ground, the friction of the ground will stop me. But if I'm in space and I start moving, nothing's gonna stop me. There's no air, there's no friction, so I'll just keep going. So if I'm orbiting the sun, then I'm just gonna keep orbiting the sun.
Why does the Earth spin around so much?
Why does the Earth spin around so much? I know, doesn't it get dizzy? It's the same kind of thing. It's because the Earth was formed spinning. And it probably formed spinning because the Earth, I mentioned when we talked about how Pluto was formed, we talked about how the Earth formed from other smaller planetesimal baby planets smashing into each other. Well, all that smacking together started the Earth spinning when it was young. And again, there's no friction, there's nothing really to slow it down. So when it started spinning because of how it was born spinning. And then there's nothing to stop it, so it's just gonna keep on spinning.
Together.
Well, that's a good question. Are Neptune and Uranus close together? They're next door neighbors, right? But they're very far apart compared to like the distance between Earth and Venus and Mars. Like these guys are near neighbors compared to the outer planets, Uranus and Neptune. As you get farther from the sun, there's much more distance between the planets. So I guess it depends on what you consider far apart. If you're talking about the distance to the stars, then Neptune and Uranus are really close together. If you're talking about the distance between Earth and Mars, then Neptune and Uranus are really far apart. So it's kind of like asking, like, are you big or are you little? If you're comparing yourself to a little worm, then you'd be like, I'm really huge. If you're comparing yourself to Shaquille O'Neal, then you'd be like, I'm little, right? So it's the same thing. It depends on what you mean by close or distance. Yeah. Which planet is what? The first one?
First planet.
That's an interesting question. I guess it depends on what you mean. Like first, like the best one, that would be, in my opinion, Earth, but I'm biased because I'm from here. Maybe you mean which one formed first, which one started first. That's what you mean. They were all born together. It's like a litter of puppies, when they're all like born at the same time. The planets were all born out of that same cloud of material, all about 4.5 billion years ago. So really, none of them were really first. They all kind of formed together at the same time. I see a hand up right here.
So we're starting to find out what the atmospheres of exoplanets are made of. What would we need to do to find out what the atmospheres of moons going around exoplanets?
That's a good one. So the question is, we're starting to find out what the atmospheres of exoplanets are made of. What he means is, it's not just the planets on our own solar system that we know about anymore, the ones that I showed on that picture before. There's also all of these new planets we're discovering around other stars. Those are the exoplanets, which is really cool. Now, instead of just 9 planets or however many you want to count, we know about billions and billions because we know about all the planets around other stars. But it's very hard to discover what their atmospheres are made out of. But the way we do it is we look at the starlight that's shining through that atmosphere and the way that atmosphere filters that starlight. And sometimes we can tell because the color of the light's a little bit different when it comes to that atmosphere. You can tell what gases are filtering it through. So how are we going to find out about the moons? Well, ultimately, we can do the same thing. The moons are orbiting, it's going to be harder, but the moons are orbiting the planets, and the planets are orbiting the sun. So if a planet has a big atmosphere, then there'll be some geometry, some arrangement where that light from the sun is coming through the atmosphere of the planet and through the atmosphere of the moon, and that will oscillate with the moon's orbit, right? So I think it'll ultimately, potentially you could do it with the same technique, but it's not gonna be easy, right? Yeah. There we go.
Could humans, live and survive on Venus?
Could humans live and survive on Venus? It's not gonna be easy, but if you had asked me, could humans live and survive in Antarctica? If you had asked me that sometime in the past, I would have said, I don't know, I don't think so, but now people do live there, right? So using technology, and the kind of thing that Dr. Sharp was talking about earlier, we can live places where you couldn't live without technology. So maybe someday, I mean, it's very hot on Venus, so you would need a really good air-conditioned environment, right? But the other thing on Venus is maybe we can live up in the clouds someday. Because on Venus, on the surface, it's really hot, but up in the clouds, it's kind of cool. I mean, cool like, hey, man, it's cool, but also like cool, like it's not too hot. So maybe someday we can have a floating city up in the clouds of Venus. What do you think? Should we try that? Yeah, okay.
So I'm gonna have us do just one more question, okay? But I'm sure Dr. Focus will be having to hang around afterwards.
I'll hang around. I'm getting cut off here.
Yeah.
How are black holes invented?
Black holes?
Yeah.
How are they made? Okay, so black holes are very, very strange, and hard to believe they're real, but they are real. And basically, when you have a star like the sun, at the end of its life, it uses up all, a star is a big nuclear reactor that's burning up hydrogen, right? And putting out light. At the end of its life, it's used up all its hydrogen and it's burned up most of the material in it. And it explodes, or some stars, eventually they collapse. Now, the sun itself is never going to be a black hole because it's not massive enough. But a really massive star at the end of its life, because of all that gravity we were talking about, it will collapse and collapse and collapse into itself and get smaller and smaller, and the gravity gets stronger and stronger and stronger. And if there's enough mass there, it's a very strange thing, and it's hard to describe and it's hard to understand. And I can't say I even really understand it myself, but there's just so much mass and it just collapses so much that nothing can stop it. It keeps going to the point where it doesn't have any size at all anymore. And it's so much mass, so much density, it's sort of infinite mass, and it basically punches a hole right into space. And it gets so dense that not even light can escape it anymore. And that's basically how a black hole is made.
Let's go ahead and give Dr. Clemson a round of applause. And if you have a few more questions, I'm sure he'd be happy to answer them. I'm going to encourage you, if you haven't already, to go out and look at the telescopes. They're Jupiter and Saturn are out right now. It's amazing. Thanks very much tonight for coming, everybody.
Yeah.
When did Pluto drop?
Oh, when did they change the definition of Pluto, you mean? That was in I think 2000. So it was like 16 years ago. What do you think? Is Pluto a planet? Well, there's more than one way to look at it. No. Nothing changed about Pluto. They just decided to change the way you define planet. It didn't change at all. It's just some scientists said, well, what happened was they started discovering many other objects out around where Pluto is and farther than Pluto that were sort of like Pluto. And some scientists said, well, these can't all be planets because then there'd be too many planets. Which I think is sort of silly, but that is what happened. And they said, okay, we're going to change the way we define planet a little bit so that there's only 8, and we'll call Pluto something else. So it was nothing changed about Pluto. It was more that we just started discovering other objects, and then they said, well, let's change the words we use. There's just a change in the words we use. Yeah. Does that make sense? Yeah. Cool. Yeah. There you go. Want me to sign that?
I think you brought one of your stickers.
Oh, weird. Thank you.
There you go.
And also, I have a question.
Yeah.
What did you think about white holes? Like, do you think they exist, and do you think that they're wormholes, or do you think they do something else?
Wait, what was the first part? What do I think about?
Like, if you think white holes exist,
Oh.
what do you think they do?
Oh, is that, yeah, I don't know. That's a good question. I think that we still don't know. They could exist, but I think that we're still, some science questions, we just have to be honest and say we don't know the answer yet. And I think that's one of them.
I have a question.
Yeah.
Like, what could happen if like a black hole sucks up a white? Like, would it explode? Would it like become a white hole? Would the white hole become a black hole?
That's a really good question. Honestly, I don't know the answer to that one. I'm sorry. I don't know everything. I know a lot. You know a lot, but I don't know everything, and I don't know that answer to that. You too.
Why do Earth has gravity, but space doesn't have it?
Oh, because there's nothing in, like, if you're in somewhere in space where you're not on a planet, there's nothing there. In order for something to have gravity, there has to be mass, has to be matter. So if you're away from a planet and you're, the only way you have gravity is like, it's like a property of matter. You need matter to have gravity. So out in space where there's no matter, then there's no gravity. Yeah. Of course. Selfie. Let's do a selfie. Here, want to hold up the Sky News? Sure. What's your name? Aletta? Elena. Nice to meet you. Yeah. Sure. Hi. Oh, you want an autograph? Sure. Yeah, of course. Of course.
Part of these guys?
Oh, thank you.
I work for.
Wait here, I'm gonna put my deluxe autograph for you because Dr. Funky Spoon is my other name. There you go.
We're having a
Yeah.
professional astronomy conference at the RBC Center.
Well, it depends on how fast you go. That's what I'm saying. How long is it gonna take to get to Toronto? If you're, in a jet airplane, it's gonna take half an hour. If you're walking, it's your like.
This is
So
just one of the
astronauts and their
events
rockets,
that's being.
Several days. But the New Horizons spacecraft that went to, how long did it take New Horizons to get to the moon's distance?
Oh, like 16 hours,
So see, so it depends on how fast you're going. The New Horizons,
9 hours, something like
yeah.
that.
Whereas the astronauts, it took them like,
It took them like 100 hours.
yeah,
So it's going like 10 times. the speed.
yeah. So it depends on how fast you're going.
Thank you so much.
Sure.
We have it in a
Yeah.
different place every year, usually where there's some local astronomers who offer to, organize it. And it happens to be.
Look at this slide that you use because it's really profound. Today, Mars is a frozen desert, not a frozen dessert. Spelling is important, kids.
So are you? Are you? Astronomer or?
Yeah.
Had to do something.
What kind of stuff?
I'll give that a talk some other time.
Well, I thought it's not.
gonna be your top? The dessert?
That would be.
But that was not.
Move the Canada, up to Canada.
Yeah.
Last year. But it's a go.
Oh, wow. Yeah.
So the Downtown, I spent all my time looking for.
Spaceship, right?
Space station. Yeah. It's pretty cool to see. Oh,
Yeah, there was all
so that's what that is.
Makes it a whole lot easier, doesn't it?
Yeah, so that's what I was looking for. Yeah. Climbing around there.
Yeah. I've got, I've got a couple of stuff, but the one that I use and use a lot is just, kind of simple, but I mean, it's a go-to and so take some pictures. For some reason, I thought it was in the summer.
Yeah. And I got it a year ago. Got told. It's fine. It's sold.
At least. Yeah. But it's winter outside now, right? Yeah. I'm gonna actually head out. Have you seen the setup we have out there? I did. There's a lot of people and. Yeah. I haven't still. You've seen people. Yeah, I wasn't that interested in. Although I did see the one guy. Yeah, he had a. Well, he had a bigger than that, you know? Well, the ones I had, a 15, 16 inch, wood shop, yeah. But he got this, the last guy, he never. Oh, shit. Oh, yeah, yeah. Like sometimes honestly, like, that's kind of what I do too. If you just that, you know, rough along is fine. Sort of. All right, what's your name? Michael. Henry. Good to meet you.
About that. We do like. Do you have a question? I'm sorry. I hope.
Hey. Sure, for sure, if you want, you know.
No. Go into space. So I work with spaceships, but I stay on Earth and I send my spaceships up in the cameras and they send it down fast. I don't go into space. Are you? You guys are gonna be astronauts? Oh my God, that's so cool. No, we're trying about one. Yeah. I'm famous for myself, but not everybody. What about you? It kind of said. Center of the galaxy. So the Milky Way galaxy is it's like a disc-shaped cloud of hundreds of millions of stars, and we're like, if this is can I draw?
Yeah.
Oh yeah. Here, how about on this? This will work better. So.
Let's see. This is not yours. This is yours. It is yours. I'm sorry. Okay, great. That's your pen. And I think probably.
Like the algorithms on Facebook are pretty dangerous. Everybody's thinking of this, but in fact, it's not. So are you? I mean, I say.
Oh, you thought it was it. There was a big.
Thank you.
So I'm a planetary scientist. The American National Vision. So we have our. And we always have something. But this year we got. That's why. That means, I live down in the west. Yeah. Not many people have it. Okay. Oh, yeah.
Oh, thank you. Yeah, that's very nice.
Let me return this pen.
I've won 2 different awards from 2 different organizations. Yes, it looks like on my CV. No, not this one.
It's a very rural place with a lot of national.
Yeah, then I did get that.
And then,
Yes, they did get it like that. So, yes, I have exactly. Yeah. And also from another.
And I live in Boise. I live in Boise, which is the big city where I know. Actually, what's the
Other.
about the same size as mine. It's about the same size as mine. It's kind of New York City. But you know, half like.
I was getting in actually run around. Yeah, it's actually making it stupid. Like,
Yes.
Great.
Yes.
I had a thought.
Not quite. Yeah, yeah. Yeah.
Well, they're actually both in college.
Yeah, I mean, you have like.
Biggest
I'm steering the university.
Yes.
Bad.
They really.
I can tell you. Yeah, well. Honestly, we didn't believe it was.
Yeah. Yeah, I have to.
Yeah. Coming out. Yeah, you know. Should be easy.
Henry, taking off?
I wanted to.
I was gonna probably.
Okay, cool.
I have a secret, like, actually don't.
Yeah, it's like out there and then it's just around the corner.
But I love
That's why I was trying to.
Okay, yeah. Thank you. Yeah, no, I wish I could stay a bit longer. It's just-
Well, that's pretty big. Some trouble getting on the flight last night. So I had to come in this morning, so.
That's great. Made up time.
Okay.
Sitting there. All right. No, I'm actually.
Oh, that's the conference.
Yeah. Which is very strange. It's like very big.
Yeah, no, I know, right? It was a little. When I got it. Yeah.
Figured it out. Yeah. Anyway, listen. It's like, it's really nice to.
I was in Columbia many years ago. When we first talked, but they wouldn't.
Great, yeah, nice to meet you. Sorry. I realized I wasn't.
So I can tell you what happened, right? Like literally 2 weeks ago, after 6 months, turn, we had graduated. So, you know, so I really, yeah. So, we'll have that in mind for next time. We'll be in San Antonio. We're gonna get in front of
All right. I'm gonna just think about Good to see you. Nice. Yeah.